Welcome to the deep dive. Our mission is always to help you navigate, well, the overwhelming sources of information out there, but today we're tackling a wall of material that's, well, it's literally overwhelming.
Though it is.
The massive fastener aisle at any European hardware store.
It's genuinely intimidating. I mean, you look at those thousands of little metal components, and they're all color-coded and numbered, and to the casual DIYer, they all look pretty much interchangeable.
Yeah, a screw is a screw, right?
But that's where the danger lies. If you choose the wrong one, if it's the wrong material, the wrong head, or the wrong coating, you risk, structural failure, poor joints, and premature rust that will just ruin your project in months, not decades.
So the difference between a connection that lasts a lifetime and one that fails can come down to
What?
a few microns of coating?
A few microns of coating thickness, or a really subtle difference in the thread geometry. Absolutely.
Yeah. Okay, so that's our mission today. We are taking a deep dive into three of the most absolutely essential, most commonly used European fasteners that, basically hold our world together. Whether you're building flat pack furniture or securing a massive roof panel, we're talking about the versatile chipboard screw, the highly specialized drywall screw, and the high-tech, metal-munching TEK screw.
And we're going far beyond just recognizing them by their heads. We're going to really understand the specialized anatomy, the metallurgy, those exacting European standards, and the sophisticated coatings that make these little components perform so reliably.
So we're going to dissect why a fully threaded chipboard screw has pretty much taken over from the traditional wood screw for daily tasks, even though, and this is interesting, the wood screw technically offers better clamping force.
We will.
We'll also look at why the drywall screw's unique curved head is absolutely how does a TEK screw manage to drill through structural steel without dulling its point or just snapping off? And why does one coating protect your project for 50 years while another one just flakes off after one harsh winter?
It really is all about precision engineering, just on a micro scale.
Okay, let's unpack this. We'll start with the daily workhorses that are, well, they're probably holding the desk you're sitting at right now together.
I think we should start with a chipboard screw. It's genuinely the modern multi-purpose fastener.
Right, and the name gives it away, doesn't it?
It does. Its origin, as the name clearly states, was specifically for engineered woods. So we're talking about particle board, MDF, that's medium density fiberboard, and OSB-oriented strand board.
And these materials they're everywhere. They're the backbone of almost all modern European furniture and cabinetry.
Exactly.
And that's a really critical distinction because engineered wood behaves completely differently from solid timber, right? Solid wood is fibrous, but engineered wood is. It's basically pressed fibers and resin.
It is. It's dense, but it's also really prone to splitting, especially if you try to drive a fastener too close to an edge.
I think we've all been there.
Precisely. A traditional wood screw, which was designed for that fibrous timber, it often just wouldn't perform well here. So the chipboard screw has evolved this specific superior anatomy to handle this delicate balancing act.
And what's the key feature there?
The key feature is its deep, coarse, single thread. This thread geometry is just paramount because the deep helix creates this exceptional grip and a dramatically high pull-out resistance.
So that's exactly what you need in materials that don't have that natural grain structure of solid wood to hold on to.
You got it. That's exactly it.
And compared to old-style screws, they also have a very distinct look, a really slim shank compared to the head size. Why is that specific ratio so important for engineered wood?
So that slim shank, combined with a sharp point or often a specific cutting flute, is engineered to aggressively mitigate splitting. Think about it. You're driving a screw into the side of an MDF shelf panel. You need the absolute minimal amount of material displacement possible.
Right, you don't want to blow the side out.
Exactly. The slim profile reduces that outward pressure on the material, which lets you drive the screw very close to the edge of a panel. And that sharp tip, or the specialized cutting flute, effectively makes it self-tapping.
Which often means you don't need to pre-drill.
Often, yes. It eliminates the need for a pre-drilled pilot hole, which is just a huge time saver in high-volume assembly, like, flat pack furniture.
So it's a perfect blend of high grip and low material stress. It's built for speed and minimizing the risk of destroying an expensive cabinet panel.
Exactly. Speed and efficiency are non-negotiable in modern assembly. And speaking of high-volume assembly, anyone who has put together European flat pack furniture has seen one drive type that just dominates everything.
Ah, yes, the ubiquitous cross-shaped driver that doesn't quite look like a regular Phillips head.
That is the Posidriv, or PZ. Now, while the standard Phillips, or PH, is known globally, Posidriv is particularly common across the European Economic Area, especially for furniture.
What's the difference in the design?
The PZ design adds 4 extra contact points that radiate out from the center, which gives it deeper and more effective engagement compared to a standard Phillips recess.
And that's crucial for preventing cam out.
It is that dreaded moment when the bit slips out under torque. It's a major problem when you're driving into dense materials like chipboard.
I hate that feeling and that sound.
We all do.
And for higher performance jobs or professional work, Torx is becoming the standard now, isn't it?
Yes, the TX drive. Torx is superior still. It offers 6 points of contact and 0 radial forces.
Meaning the force is all rotational.
All of it. It's applied purely rotationally. So if you need to drive a large structural chipboard screw or a big decking screw that requires massive torque, Torx is often the preferred choice to ensure the bit doesn't strip the head. But, Posidriv remains a historical fixture and the standard for general DIY.
You mentioned a technical footnote earlier, though, for the purists. The chipboard screw has largely superseded the traditional wood screw for speed, but the old design, it offers better clamping force. That seems counterintuitive.
It does, but it comes down to the thread geometry. A traditional structural wood screw only has threads on the bottom portion of its shank. The upper part near the head is smooth.
Okay, so a partial thread.
Right, and that smooth shank allows the top piece of wood to slide freely down the shank as the threads engage and bite only into the bottom piece. It effectively acts like a clamp.
Ah, I see. So it pulls the two boards together really tightly. It creates a powerful vice action.
Exactly. A fully threaded chipboard screw, while it's fast and efficient, can start to engage the threads in the top board too soon. As you tighten it, the threads might just be drilling into the top board rather than pulling it down forcefully onto the bottom one.
So it reduces that critical clamping force you need for high-load structural joints.
It does. So for the vast majority of non-structural jobs cabinetry, showing the chipboard screw is the clear winner for speed and versatility. But for heavy-duty structural joints, the partial thread wood screw. It still reigns supreme for pure clamping power.
That is a fascinating detail. Okay, let's transition to our next common hero, the drywall screw. These are truly specialized, and if you use them for anything other than plasterboard, you've fundamentally misunderstood their engineering purpose.
Absolutely. Drywall screws are designed almost exclusively for attaching plasterboard or gypsum board to framing studs, whether that's wood or light gauge metal. They are an excellent example of a fastener whose entire anatomy is dictated by the fragile material it's fastening.
And the most unique part of that anatomy has to be the head. It's not a standard flat countersunk head at all.
And here's where it gets really interesting. It features the critical bugle head.
The bugle head.
Yes. It looks like a shallow curved funnel or a trumpet flare. Imagine trying to push a nail into paper. If the nail has a sharp, flat countersunk head, it acts like a miniature chisel and just slices the paper immediately.
Okay, and with drywall, that outer paper layer is everything.
It provides the majority of the board's structural integrity.
So the bugle head is designed to apply pressure gently.
Precisely. Its curved geometry is designed to depress the paper facing and the gypsum core, creating that perfect little dimple for the joint compound without tearing the paper.
Ah.
If you tear that paper layer, the connection fails almost immediately when any stress is applied. The bugle head creates an indentation, allowing the screw to sit flush or slightly below the surface for mudding, but it keeps the integrity of that structural paper layer completely intact.
That's fantastic specialized engineering. It's a design dedicated entirely to not destroying the material it's meant to hold.
It is.
Now, we touched on the fact that you need different thread types depending on what the drywall is attaching to.
That's right. Drywall screws are categorized by the substrate. You have coarse threads, often labeled W-type, which are designed for wood studs.
W for wood.
Exactly. The wide gaps in these threads help them aggressively bite into the softer wood structure and hold fast.
And then for metal frame construction.
For that, you use fine threads, or S-type. These are optimized specifically for light gauge metal studs, typically steel up to about, say, 0.8 millimeters thick.
So much thinner material.
Much thinner. The finer pitch provides a lot more thread surface area for reliable engagement in that thin metal substrate. Using a coarse thread on thin metal wood, well, it would strip the metal almost immediately. You need that fine pitch to maintain engagement.
And we noted the finish, they are famously black. What is that coating doing besides just making the screw look moody?
That black coating is almost universally black phosphate, and it serves multiple crucial roles for this specific indoor application.
Okay, what are they?
First, it provides basic, mild corrosion resistance, which is fine for dry indoor environments, what we call C1 or C2 environments. But its critical specialized function is that it's chemically compatible with the gypsum, the plaster, and all the jointing compounds used in the finishing process.
Why is that compatibility so vital?
Well, if you used a standard bright zinc-plated screw, for example, the zinc coating could react chemically with the alkaline components in the gypsum and the joint compound.
And that would cause problems later.
It would. This reaction often leads to visible rust spots or discoloration bleeding through the paint on the finished wall surface, sometimes weeks or even months after the job is done.
Ah, a nightmare for a decorator.
Absolutely. The phosphate coating prevents this chemical interaction, ensuring the final aesthetic integrity of the wall finish. It's all about making sure that final coat of paint looks perfect.
It's incredible how much thought goes into something that is immediately buried under joint compound and paint and never seen again. Okay, so if the drywall screw is the master of delicate materials, the TEK screw, the self-drilling screw, is the master of efficiency in metal construction.
It absolutely is.
So detail the core function of this self-drilling technology. What makes it so revolutionary in construction environments?
Its core function is really a feat of consolidation. It takes 3 distinct construction actions: drilling, tapping, which is cutting threads into the material, and then fastening. And it combines them all into a single seamless operation.
And TEK is a trade name, right?
It is, yes. TEK is a popular trade name, but the technology is what we call self-drilling. By eliminating the need for a separate pre-drilled pilot hole, it saves an immense amount of time, labor, and tooling swaps.
Which makes it indispensable in what? Light steel frame construction.
Light steel frame construction, metal roofing, cladding, HVAC installation. Huge range of applications.
But drilling through steel requires an extremely hard tool, almost like a miniature drill bit. How does the screw itself manage that without just dulling or snapping immediately? I mean, the final fastener also has to be tough enough to hold the load.
That brings us to the fascinating anatomy of the cutting edge and the drill point numbering system. The effectiveness of a TEK screw relies entirely on its tip geometry, which is standardized. The drill points are classified using a numbering system, typically ranging from TEK number 1 to TEK number 7.
Okay, explain that numbering system. What does a higher number signify in practice?
The numbering classifies the screw's drilling capacity. It relates directly to the maximum thickness of steel it can penetrate. A TEK number 1 or number 2 point is suitable for thin sheet metal or aluminum.
And a higher number?
A higher number, say a number 5 or number 6, indicates a longer, more robust point that's capable of penetrating thicker or significantly harder structural steel, sometimes up to 12 millimeters of steel plate.
Wow, that's a huge difference in capacity based purely on the tip geometry.
It is. And regardless of the number, there is a critical inviolable engineering rule that has to be met for these screws to function correctly, particularly in multi-layered assemblies.
And what's that?
The unthreaded pilot section of the point must be long enough to drill completely through all layers of material before the first thread engages.
So it's a race between the drill point and the threads.
Exactly. If the threads engage prematurely, say, before the point has fully cleared the material, the screw just binds up instantly.
And then what happens?
When that happens, the torque required to continue driving jumps dramatically, which leads to excessive torsional stress. The screw is almost guaranteed to shear off or fail catastrophically right at the juncture between the head and the shank.
So that critical time delay is engineered right into the length of that pilot section.
It is. It's a self-timed, self-regulating mechanism that's engineered into the geometry itself. Truly brilliant.
It is. Now, let's go back to that material science challenge. How can a single piece of steel have a point that's hard enough to cut, say, HRC 40 steel, but a body that's soft enough not to snap off under the high torque needed to drive it? That sounds like a contradiction.
This is where we can really appreciate the genius of differential heat treatment, specifically case hardening.
Okay.
As you pointed out, you need 2 distinct conflicting material properties. The point must be extremely hard, a high Rockwell hardness, typically HRC 52 or more, to effectively cut steel without dulling immediately. If it's too soft, it just won't penetrate.
But if the whole body were HRC 52, it would be as brittle as glass. It would snap the moment it encountered a lateral load or sudden torque.
Precisely. And that's where the body, or the shank, must remain softer and more ductile, typically somewhere between HRC 28 and 34. This toughness is essential to resist the high shearing forces and twisting during installation and prevent that catastrophic torsional failure.
And differential hardening achieves this balance, so how do they stop the heat treatment from spreading to the whole body?
It's controlled through the manufacturing process. It often involves introducing carbon, a process called carburizing, but only to the areas that are intended for hardening. And then they use very precise heating and quenching processes.
So you end up with a hard outer case around the point.
A hard wear-resistant outer case around the point and threads, yes, while the inner core, the majority of the shank, retains its shock-absorbing ductility. That balance extreme hardness for cutting and high ductility for strength is what makes the TEK screw a marvel of modern engineering.
And of course, a product that's engineered is heavily standardized, especially in the European market.
Absolutely. TEK screws fall under the DIN 7504 family of German standards, and many of those have been harmonized into ISO equivalents for cross-border compatibility. Understanding these standards tells you exactly what purpose the screw is designed for.
So let's run through the key family members the listener might encounter in a professional context.
Okay, the primary industrial workhorse, especially for applications like metal roofing, cladding, and structural steel connections, is the DIN 7504K, which is also standardized as ISO 15480. The K stands for the hexagon washer head. It's recognizable by its protruding industrial appearance, and it's designed for high clamping force and easy driving with socket tools.
But what if you need a flush finish?
Then you move to the DIN 7504P, or ISO 15482, which is the countersunk head. This is used where the fastener needs to sit flush with the material surface, like in high-quality metal enclosures or vehicle bodywork.
Okay.
And for general light assembly, like ducting or enclosures where visibility is less of an issue, we see the DIN 7504N, or ISO 15481, which is the pan head. It provides a low, rounded profile.
Now, when we talk about roofing and cladding, we inevitably see TEK screws that come pre-fitted with a washer. We learned earlier this is a sealing component, not just a standard washer.
That's right. This is the fourth component in the system. We're talking about bonded EPDM washers.
EPDM, what is that?
EPDM is ethylene propylene diane monomer. It's a specialized synthetic rubber, and its selection is absolutely critical.
Why EPDM specifically? Why not just regular rubber?
Because of its extraordinary resilience against the elements. A roofing seal needs to last for decades under constant stress. EPDM resists UV radiation and ozone breakdown, which are the main killers of cheaper rubber compounds.
Right.
It also handles extreme temperatures, often rated from -50°C up to +150 degrees. This prevents the seal from drying out, becoming brittle, cracking, and failing prematurely.
Which is the immediate cause of water getting into a structure.
It is. So the metal washer distributes that high clamping force, and the EPDM provides the flexible, weather-resistant barrier.
Exactly. And this leads directly to a crucial installation note. The performance of this system is 100% reliant on proper torque.
Okay, so how do you know you've got it right?
Proper installation means achieving a slight mushroom shape in the EPDM washer as it's compressed against the sheet metal. This is the visual confirmation of a watertight seal. And what happens if you get the torque wrong?
Failure. If you under-tighten, the rubber doesn't compress enough, the seal isn't formed, and water leaks in. If you over-tighten, you strip the threads in the thin metal substrate, or worse, you squeeze the rubber out from under the metal washer, creating a paper-thin seal that will tear or degrade rapidly.
So both scenarios lead to water damage and structural issues over time.
They do. You need the perfect balance, which usually requires a clutch-equipped power tool set to a very specific torque value.
Okay, we've covered the mechanics and geometry of these fasteners, but the real foundation of their durability is the material itself and how it's treated and manufactured. Let's start with the base metal choices you encounter when choosing a fastener.
In the world of common construction and DIY, the choice usually boils down to two options: carbon steel or stainless steel.
Okay.
Carbon steel is the economical workhorse. It's the most common and cost-effective material, typically using low-carbon grades. However, and this is the big catch, it is highly susceptible to rust. It must be coated.
And if that coating is the only thing protecting it, a single scratch makes it vulnerable.
Precisely. Now, contrast that with stainless steel, which is the premium choice. It's inherently corrosion-resistant because of the self-healing chromium oxide layer that forms on its surface when it's exposed to air.
Self-healing.
Yes. Even if the surface is scratched, provided the environment isn't too harsh, that thin oxide layer regenerates instantly, unlike a coating, where a scratch just exposes the vulnerable core.
And there are different grades even within stainless steel that reflect its resistance profile. This is critical for the listener choosing the right fastener for an environment.
It is. The most versatile and common grade is A2. also known as Type 304. It offers excellent corrosion resistance in freshwater and normal atmospheric conditions. It's the standard for outdoor furniture, general decking away from the immediate coast, and indoor applications like commercial kitchens or bathrooms.
But if you live in a coastal area near the sea or near a swimming pool with harsh chemicals, A2 will eventually fail.
It will. A2 is highly vulnerable to chloride attack, which causes a failure mechanism called pitting corrosion. For those environments, you absolutely must step up to A4 or Type 316.
And this grade is alloyed with molybdenum.
Molybdenum is the key addition, yes.
What does that do?
Molybdenum provides superior resistance to chlorides and salt water. A4 is essential for coastal decking, marine contexts, or industrial environments with chemical exposure. That little bit of molybdenum is literally the difference between a fastener lasting 10 years or 50 years in a high salinity environment.
A critical distinction, A2 for inland, A4 for the coast. Now let's delve into how carbon steel can be, well, supercharged for high performance without the cost of high-alloy specialty steels. This involves a fascinating topic called microalloying, specifically the boron effect.
This is really cool stuff. We often see standard carbon steel listed as C10022. That's the workhorse reliable, but not exceptionally strong. Then you might see C10B21.
And the B stands for boron.
It does. C10B21 is chemically nearly identical to C1022, except for a minuscule addition of boron. We're talking fractions of a percent.
So a tiny amount of boron changes everything. How does that work metallurgically?
It's a total game changer because of what it does to the steel structure during heat treatment. This tiny addition grants C10B21 steel exceptional hardenability.
Hardenability. And that refers to the depth and consistency of hardness that can be achieved when the steel is quenched or rapidly cooled after heating.
That's it. The boron allows the heat treatment process to penetrate deeper and more effectively.
Okay, so what's the implication?
This microalloying strategy allows C10B21 screws to achieve very high strength levels, like property class 8.8, that are usually comparable only to much more expensive high-alloy steels. It provides cost-effective high-strength performance.
So a designer of, say, a structural truss connector or an automotive component would love C10B21.
They do. They get high tensile strength and load-bearing capacity without the material cost premium. This allows for smaller, lighter, and yet incredibly strong fasteners used in millions of units of high-volume assembly.
That's incredible. It shows that fastener technology isn't just about shaping metal, it's about controlling the atomic structure with trace elements.
It is. And the final piece of this metallurgical puzzle is how the thread itself is manufactured. This dictates its ultimate resistance to failure under the mechanical stress of its long life.
So now we're talking about thread rolling versus thread cutting.
Right. Thread rolling is the method used for any high-performance fastener, and for the vast majority of commercial screws like our chipboard and TEK screws. It's a formative process. It displaces the metal using hardened dies rather than removing it.
Okay, so like taking a piece of soft clay and pressing a groove into it, the material flows.
Exactly. And that flow is critical to strength. Thread rolling forces the grain structure of the steel to flow continuously along the thread contours, mirroring the shape of the thread root and crest.
And this continuous grain flow is a massive enhancement to durability.
Massive. It could increase the fatigue life by 5 to 10 times and boosts tensile strength by 10 to 30%.
Now contrast that with thread cutting.
Thread cutting is a subtractive process, like using a lathe or a machining tool. This process severs the grain flow, essentially slicing through the metal structure. This immediately creates stress risers.
Microscopic notches.
Right. If you think of bending a piece of wood, it's strong. But if you cut a small notch into that same piece of wood and bend it, it breaks instantly at the notch. Those stress risers are where fatigue cracks easily initiate and grow under cyclic loading.
Ah, so we are now entering the territory of fatigue, the true invisible killer of structural connections. This is where the initial thread manufacturing matters years down the line.
Exactly. Fatigue is the progressive, localized structural damage that occurs when material is subjected to repeated fluctuating stresses, even stresses well below the yield strength of the material. A well-rolled thread drastically minimizes the chance of that crack initiating.
If thread rolling is so good at building in strength, when should that process happen relative to the heat treatment?
This is a point where material engineers get very, very specific. To maximize fatigue resistance, the thread should be rolled after heat treatment.
After? Why?
This preserves and, more importantly, it induces beneficial compressive residual stresses at the thread root.
Compressive stress sounds like a good thing.
It is. Residual compressive stress is essentially pre-stressing the material. When the screw is later placed under tension or cyclic loading, the external tensile load has to first overcome that beneficial internal compressive stress before the thread root actually experiences true tension.
So if you do the rolling before the heat treatment.
The high temperatures of the heat treatment process will relieve those beneficial residual stresses, largely negating the anti-fatigue benefit. The sequence matters immensely for the final product's ability to resist failure over decades of service.
Since most of our workhorse fasteners are made of carbon steel, the coating is the single most important factor determining longevity and cost-effectiveness. This is where we see a huge spectrum of value.
A huge spectrum, yeah. From virtually zero corrosion protection to systems designed to last half a century.
So let's establish the hierarchy of zinc coatings, which are the most common defense against rust.
Right. Zinc is used because it acts sacrificially. If the coating is scratched, the zinc corrodes preferentially to the underlying steel, protecting the core.
At the low-cost end, we have the shiny screws you might grab for an indoor repair.
That is zinc plating or electroplating. It's a low-cost process that results in that bright, shiny, almost chrome-like finish. But critically, the coating is extremely thin, typically only 5 to 10 micrometers.
And that thinness provides minimal protection.
Minimal. It's suitable only for dry indoor use, classified as C1 or C2 environments under the ISO standards. If you use this outdoors, the expected service life is only 1 to 2 years before the rust begins.
So you trade long-term durability for low initial cost and a nice look.
That's the trade-off. Next, we have the gold standard for long-term outdoor protection in structural applications. Hot dip galvanizing, or HDG.
And that's a completely different process.
Completely. It involves immersing the fastener in molten zinc at about 450 degrees Celsius. This high temperature causes the zinc to react metallurgically with the steel, creating a thick, multi-layered coating that is permanently bonded to the steel substrate.
That metallurgical bond sounds significantly more robust than a simple plating.
It is, and the thickness is the key. HDG results in a much rougher, dull gray finish, but the coating thickness is substantial, typically 45 to 80 micrometers.
Wow.
For structural outdoor applications, so C3 or C4 environments, a minimum HDG thickness of 45 to 55 micrometers is essential. Because thickness is directly proportional to service life, this provides an expected service life outdoors of 50 to 70 plus years.
So despite the higher initial cost and rougher look, it is by far the best long-term value.
By far.
And what about that third method, which is less common in DIY but vital for high-strength steel?
That is mechanical galvanizing. This is a medium-high cost niche option. It's a room temperature process where fasteners are tumbled with zinc powder and glass impact beads, which cold welds the zinc onto the surface. It produces a matte, silvery gray finish.
And what's its main advantage?
Its main advantage is that it avoids a critical safety risk inherent in electroplating: hydrogen embrittlement.
That sounds dangerous. What is hydrogen embrittlement and why does electroplating cause it?
Hydrogen embrittlement is a silent killer in high-strength fasteners. During the electroplating process, trace amounts of hydrogen atoms are absorbed into the crystal structure of the steel. Because high-strength steels are inherently harder and have a less ductile structure, these hydrogen atoms interfere with the internal bonding.
Leading to a dramatic loss of ductility.
Exactly. The fastener can be installed successfully, but under subsequent stress, sometimes days or weeks later, it cracks catastrophically without warning.
So if you have a high-strength fastener like a structural grade bolt, you absolutely cannot use standard electroplating.
You should avoid it, or you must follow extremely stringent post-making processes to drive the hydrogen out. Mechanical galvanizing bypasses this risk entirely because it's a cold process that doesn't generate hydrogen, making it the safer, reliable choice for property class 8.8 and higher fasteners used in critical applications.
Moving beyond pure zinc, we see manufacturers developing highly complex multi-layer coating systems.
Those are the advanced coatings, often categorized as zinc flake coatings like Geomet or Rustbert. Geomet, for instance, is the environmentally responsible, chromium-free evolution of an older technology called Dacrymet.
And that's crucial because of EU regulations.
It is. It complies with stringent European Union regulations like RoHS and REACH, which strictly restrict toxic substances like hexavalent chromium, which was previously used to boost corrosion resistance in older yellow zinc coatings.
So Geomet is high performance, but also compliant with modern EU sustainability and safety mandates.
Exactly. And Rustbert is another impressive multi-layer ceramic hybrid coating. It not only offers phenomenal corrosion resistance, often C4 or C5 rated, but it also provides superior abrasion and damage resistance.
So it's tougher.
Much tougher. This makes it highly recommended for severe construction and marine environments where fasteners might face mechanical damage during installation or be exposed to abrasive forces like wind and sand.
All of this performance and reliability is tied back to European standards. You can't just sell any old screw across the European Economic Area. The standardization dictates quality and safety.
That's right. The European market has seen a major evolution, shifting away from specific national standards like the German DEN standard, say DEN 965, for a specific countersunk screw-to mandatory international ISO and harmonized European EN standards, like ISO 7046.
And adherence to the current EN and ISO standards is the price of entry.
It is. It guarantees safety and, critically, interoperability across the single market.
And for anything structural, the manufacturer needs more than just a standard number. They need a mark.
That's the mandatory CE marking. The CE mark is the manufacturer's declaration that the product complies with all applicable EU health, safety, and environmental requirements. But for critical structural fasteners, like large lag bolts or specific TEK screws used in public works, this often requires a European Technical Assessment, or ETA.
What exactly does the ETA process provide that a simple ISO standard doesn't?
The ETA is a rigorous third-party certification process. It thoroughly tests and specifies the product's actual demonstrated performance data.
So things like precise load capacities?
Precise load capacities pull out resistance values for specific materials, shear strength, required minimum edge distances, all of it. It's a critical document for engineers specifying safety-critical fasteners because it moves beyond theoretical material properties and provides quantified performance data.
So the ETA provides the technical basis for the manufacturer to legally declare conformity and affix the CE mark for structural use.
That's it in a nutshell.
Finally, we need to connect the coating choice back to the environment. The ISO classification system helps the listener match the screw to the project location.
Yes, the ISO corrosion classes, from ISO 12944. This system guides material selection based on how corrosive the service environment is. It ranges from C1, which is very low corrosivity, think heated, dry indoor spaces like offices, all the way up to C5.
And C5 is very high corrosivity.
Think constantly damp, salty industrial or marine areas.
Give us a middle ground example. Where would C3 be used?
C3 is generally classified as medium corrosivity. This often applies to protected outdoor environments or moderately polluted urban or industrial areas. So think a covered exterior balcony railing or a building in a moderate suburban environment where the exposure isn't constant salt spray.
And for a C3 environment, you'd need.
For C3 environments, you typically need a high-quality zinc flake coating, or HDG with a good minimum thickness, around 45 micrometers.
So if you're building an indoor bookshelf, C1 or C2 compatibility is fine, meaning standard zinc plating is adequate. But if you're building a structural timber frame on the coast, you need a C4 or C5 rating.
Absolutely. For that C5 coastal structure, standard zinc plating would fail in months. You would absolutely need heavy hot-dip galvanizing or A4 stainless steel. Matching the coating and material to the ISO class is the only way to achieve the promised multi-decade lifespan of your structure.
This deep dive really underlines that there is no such thing as a generic screw. Every feature, from the single-thread helix to the thickness of the coating, is a deliberate, highly engineered choice driven by the laws of chemistry and physics.
That's right. We detailed the three workhorses of modern European construction. The chipboard screw, engineered for high pull-out resistance in composite woods, relying on its coarse thread and slim shank.
Right. Then the drywall screw, defined by its critical bugle head and phosphate coating, ensuring plasterboard integrity and a clean finish.
And the TEK screw, the efficiency champion, achieving single-step metal fastening through the marvel of differential hardening.
And we saw that ultimate strength comes not just from the base material, but from these subtle, expensive processes, whether it's that little bit of boron in C10B21 steel that boosts hardenability, or the continuous grain flow created by threading the steel after heat treatment to maximize fatigue resistance.
And we also confirmed that longevity is entirely dictated by the environment, requiring us to match the fastener's coating to the appropriate ISO corrosion class. The difference between a 2-year zinc-plated life and a 70-year HDG life is a matter of micrometers and temperature, all designed to resist corrosion.
We introduced the concept of fatigue failure earlier, noting it as the invisible killer caused by repeated stress cycles, and we saw how thread rolling is the first defense. But the ultimate defense against fatigue failure is not inherent in the screw itself, is it? It's in how it's installed.
Exactly. While corrosion is the most common visible killer, the vast majority of mechanical failures in service, particularly in dynamic systems, are actually due to fatigue. And the single most effective defense against fatigue failure is achieving the correct preload or clamping force during installation.
Explain that connection one more time. Why does tightening the screw correctly protect it from the stress it encounters later?
When a joint is properly preloaded, meaning the screw is tightened correctly to its specified torque, the fastener is kept under a high static tensile tension. It acts like a very, very stiff spring.
Okay.
So when external cyclic loads are applied, say vibration on a bridge component or wind stress on a roof, the joint is so tightly clamped that the load is primarily absorbed by the clamped material itself. The bolt only experiences a tiny acceptable fraction of that alternating stress.
So the preload essentially minimizes the fluctuation of stress on the fastener itself.
It does. Insufficient preload, however, allows the joint to shift and move. This subjects the bolt to high alternating stresses, high tension, low tension, high tension, low tension, which is a direct invitation for a fatigue crack to begin at that thread root stress riser.
And the failure of one small, under-tightened, or corroded bolt can initiate a cascade of catastrophic events.
It can. Your project's ultimate safety relies on that perfectly calibrated clamping force.
So what does this all mean for you, the listener? The next time you grab a screw, don't just look at the price tag or the shiny finish. Look at the coding, understand the standard number, and remember that safety and durability rely on a few perfectly engineered millimeters of steel installed with the correct torque.
Build it once, build it right.
Indeed. We'll see you next time on The Deep Dive.